Just give it a test. It's fine.
Yeah.
Yeah. Okay. Thanks.
Okay, so the next and last speaker of the session is Lootens from Ghent, and he will be talking about Morita equivalence as a quantum circuit. So please.
Yes. Thanks, David, and thanks to the organizers for allowing me to present here and for organizing. Well, going through the effort of organizing this in person. So I will be talking a bit about, well, Morita equivalence as a quantum circuit. I realize that most of you probably are not very familiar with what that word would mean, but the hope would be that you at least understand what this is at the end of this talk. So this is actually a merged talk based on those first two papers, where the first one we were able to write down a constant depth quantum circuit that maps between Morita equivalent stringnet states. This is together with Bram, Vancraeynest-De, Norbert, Schuch, and my advisor from Verstraete. And then also this other paper, matrix products, operator symmetries, and intertwiners in stringnets. And this is joint work with Jürgen, Fuchs, Jutho, Haegeman, Christoph, Schweigert, also Frank. And then I added on, I was very sneaky, and I added on this additional talk, which is pretty much the most interesting application of this second part. And this is work we did with Clément Delcan, Gerardo Ortiz, and also Frank. So since this talk is about topological phases and mapping between topological phases, just some background. So what are topological phases? We already heard quite some things, so just to recap. These are phases that go beyond Landau's paradigm of symmetry breaking of local order parameters. So what is the situation? In 1 plus 1D, there is no intrinsic topological order, as we already heard before. Some people would argue that if you include fermions, that there would be some topological order there. I will not be talking about that. But you do have symmetry protected topological order in 1 plus 1D. So if you enforce that your states have a certain symmetry, then you will find that there is some kind of topological order there. In 2 plus 1D, the situation is different. So there is intrinsic topological order in 2 plus 1D, and that is what this talk will be about. Then you also have symmetry protected topological order in 2 plus 1D and symmetry enriched, which is kind of in between intrinsic topological order and symmetry protected topological order. I will not be talking about those. But so what is the quantum information definition of being in the same phase? Two states are in the same phase if they can be related via constant depth quantum circuits. That was shown or argued in at least those three papers. There's probably many more that I missed, but those are the main ones, I think. So going now to this 2 plus 1D states with intrinsic topological order, I'm going to be talking about stringnet models. Now, what are these stringnet models that were as proposed by Levin and Wen? They are 2 plus 1D lattice model exhibiting topological order. Just to make sure, because we had a talk about chiral topological order, this is about non-chiral topological order. So these are lattice models built from commuting projector Hamiltonians that exhibit topological order. Now, what's special about these topologically ordered states? They have a ground state degeneracy that depends on the topology of the manifold. These ground states are robust under local perturbations, and for this reason, they have gained some popularity for their possible use as a quantum memory, because these things are robust under local perturbations, right? And that's what you want. Moreover, they have very exotic excitations. These excitations can have fractional statistics, meaning that if you rotate one particle 360 degrees, you don't necessarily get either a plus or a minus sign as you would with bosons or fermions, but you can get more exotic things. You can get anyons. And these anyons, if you braid them with each other, you take one anyon around another anyon, you can get very non-trivial things to the extent that for some models, you can actually perform universal quantum computation with these anyons. So the input to these stringnet models, the mathematical thing you have to put in to get this model out, is a unitary fusion category. I will be denoting this thing by D, but actually it's not very, well, this may sound a bit, I don't know how many of you are familiar with this, but it suffices to just think of this as some kind of generalization of a group or representations of a group. And actually we will need very few properties of these fusion categories. So a simple example, or the simplest example of this, would be the toric code. Now, the Hilbert space of the toric code is given by some qubits living on the edges of a square lattice. And the Hilbert space is just a superposition of all these possible configurations. And then the Hamiltonian is a sum of commuting projectors, where you have these vertex terms denoted by AV and plaquette terms denoted by BP. And what these vertex terms do is essentially they in the ground state, they force that around the vertex, you must always have an even number of qubits in the one state. Whereas this plaquette term, what it does is it forces your ground states to be a superposition of all closed loop configurations. So the ground state of this Hamiltonian is just a superposition over all possible closed loop configurations. So this is a toric code Hamiltonian, hopefully familiar to many of you. Stringnet models are just kind of straightforward generalization of that. So the Hilbert space is now spanned by labeled trivalent graphs or stringnets. And the Hilbert space is just a sum over all these graphs where you have some labels on the edges, where maybe not standard, we also include multiplicities at the vertices. This is just some extra internal degree of freedom that you have. It's more general than the original stringnet construction, but it's a very mild generalization. And the Hamiltonian is again a sum of commuting projectors. So again, you have a sum of vertex terms and you have a sum of plaquette terms, where this plaquette term is actually a sum of other plaquette terms that we will see what they are. Now, to define what these vertex terms and plaquette terms actually do, we need some properties of this fusion category. The first property is this fusion category is something that has fusion rules. So this fusion category has objects labeled by A, B, and C here. And these objects can fuse together. And the fusion of these objects is described by the fusion rules. And that's this N, A, B, C here. These are integers, so 0, 1, 2, 3. That have to satisfy this constraint here. And this is essentially saying that these fusion rules have to be associative. Now, using these properties, you define your vertex term to be the projector onto the vertices that satisfy these fusion rules. So this vertex term is just enforcing the fusion rules at every vertex in the ground state of this model. An example of fusion rules would be the Fibonacci fusion category. This is pretty much the simplest fusion category you can have, has two objects, has an identity and a non-trivial particle denoted as tau, where the only non-trivial fusion rule is tau times tau equals 1 plus tau. And actually, this very simple fusion category is already enough to do universal quantum computation. So these things are quite interesting. The vertex term is a little bit more tricky. For this, you need something called an F move. Now, an F move is basically a local relation between the two possible decompositions of a four-valent vertex. So either you decompose your four-valent vertex with this horizontal leg or with this vertical leg, and then this F move is just saying that there is a local unitary transformation that relates these two configurations to one another. This F symbol is kind of famous. This is one of the most important properties of this fusion category. And it has to satisfy an equation known as the pentagon equation. The pentagon equation schematically looks like this. If you actually work it out, there's a lot more indices. There's some sums in there. I'm not writing this, just schematically presenting it like this. And this just arises as a compatibility condition for this F symbol. If you now, one way to think of these F moves is that they essentially express some kind of RG fixed point structure, and that if you were to look at this vertex from far away, you wouldn't want to be able to distinguish whether it's resolved horizontally or vertically. So you want these to be related by a unitary. That's sort of an intuitive way of thinking about these F moves. Now, what these F moves allow you to do is to define the plaquette term as follows. So the plaquette term is the sum of these individual plaquette terms, where each of these individual terms is just defined by inserting a loop into this plaquette. And then to actually derive the action of this loop, you have to fuse this loop with the remainder, well, with the edges of your plaquette you are acting on, and then recoupling everything using these F moves. And in that way, you get actually a six-body operator acting on these six vertices surrounding the plaquette. And similar to the case of the toric code, what this plaquette term does is it forces the ground state to be the sum over all allowed configurations. So as I mentioned, this Hamiltonian is a sum of commuting projectors, which means that the ground state is simply given by just projecting some reference state onto the +1 eigenstate of all these projectors. And a simple way to do this is just saying, well, I will act with my plaquette terms on the state where I initialize all my edges to be in the trivial label. These trivially satisfy the Fusion rule, so this is an eigenstate, +1 eigenstate of this first part here. And I just project onto this with my plaquette. Now this immediately implies that this ground state admits a representation as a tensor network, which in 2D we refer to as a projected entangled pair state, or PEPS, which you can really just think of. You have this product state, so this state of all ones, which is sitting at the bottom here, and then you act with your plaquette terms, and that's these hexagonal operators, these 6-body operators. These are your plaquette terms, and these project onto the ground state to get this thing, and that's what we call that's just a tensor network representation of this ground state. This was derived by these two papers in 2009 already. Now, the topological phase of a string net model based on some UFC D is actually given by the center of D. What this means is that, as an example, the input to the toric code would be the Z2 UFC, and the output, the center of that thing, would be actually the toric code, right? So this is the thing with 4 anions, the electric, magnetic, and the fermionic excitation. Mathematically, the way of going from this Z2 to these 4 anions is called the center. Now, importantly, different string net models, D1 and D2, can have the same center. Two such categories are said to be Morita equivalent. That's the name in the title, that's where it comes from. And their associated string net models should be in the same phase, if indeed the center is a description of the phase of the string net model. And now, a very natural question that you can ask is, okay, we have this definition of being in the same phase, but we also have this quantum information definition of being in the same phase. What is the constant depth quantum circuit between two such string net models? Now, to construct this constant depth quantum circuit, we need an additional piece of data, some additional structure. And that's the notion of boundaries and domain walls in these string net models. So Kitaev and Kong argued that gapped boundaries of string net models, described by some unitary fusion categories D1 and D2, are described by a module category M. Now, all you really need to know is that this module category is some mathematical packaging for these pictures. So all you really have to understand is these pictures. So you have your normal F moves in the bulk of your string net model D1, which, again, as I said, express some kind of RG fixed points property in the bulk. Now you just generalize this to the case where you have some boundary. So this boundary now is drawn vertically, labeled in blue. These objects are objects in some different category, the category M. But again, near this boundary, you have some kind of RG fixed point move. And this comes with a different kind of F symbol, which is denoted by this F symbol with a triangle here. Similarly, on the other side of the, for the other string net model, you have some bulk recoupling condition, which we already have. And then we have some boundary to the left of the string net model. And again, we have this, this F move just expressing kind of an RG fixed point property. And now, so this is about boundaries. Now, what is a domain wall? A domain wall is just, you have a boundary to the left of your string net model D1, to the right, you have your string net model D2, and in the middle, these are compatible with one another. And that just comes with yet another additional condition, saying that this left boundary and right boundary are compatible. And if you have the structure, then you have a domain wall. And you have all these, well, this comes again with an F symbol. So in total, we have 5 different F symbols. And very similarly to the ordinary pentagon equation, this combined set of F symbols satisfies some coupled set of pentagon equations, again, just expressing the compatibility of all these things. So we have 6 pentagon equations here. Now, importantly, the notion of an invertible domain wall, if these D1 and D2 are Morita equivalents. So it's meaning that these two string models are in the same phase. You can make this domain wall invertible, meaning that at the level of these diagrams, it means that there exists some kind of resolution of the identity. But more physically, what this means is that these domain walls can be inverted, that if you move these two domain walls close to each other, you can just remove them. So you have these two properties, which you can just derive from these two diagrams. So with these properties, let's try to see how, or at least let's try to sketch how such a quantum circuit could be constructed. So you start with some string net model, ground state, denoted by this black hexagonal lattice. And in every plaquette, you insert one of these invertible domain walls. And now, very similar to how you work out the plaquette term of the Levin-Wen model, you just enlarge this, you fuse this with the edges of this plaquette. You fuse these bubbles to your lattice. And so the first step would look something like this. So you first do these guys. So I fused now all these blue loops with the edges surrounding them. And I realized that blue is a very bad color because it doesn't really contrast with black very well. But all the edges around the bubbles that have been removed are now colored blue. And then secondly, you do another sublattice. So there's these three kind of sublattices. You have to do this for the hexagonal lattice. You do the next sublattice, and this gives you this. And then you do this again, and then this gives you something like this. So you just insert these domain walls in each of the plaquette, and then you grow them. And then that way you define some operator that goes from one string model to the other string model. And this is essentially the whole idea. Now, the remainder of this is just working out the details and making sure everything is fine. But from this, you can construct an operator that maps the ground state of a string model D1 to the ground state of a string model D2. It's a depth-3 circuit. Depth-3 because there are like 3 steps involved in doing this. But this is just specific to the hexagonal lattice. If I would have taken a different lattice, there would have been a different depth. And you can extend the circuit to act on the full Hilbert space. Actually doing this is a bit technical, and this was the main technical difficulty in actually constructing this. But it's not too hard, and it's quite doable. Now, in general, the dimensions of these two Hilbert spaces of these two string models, so the ground states, they match. That's just a property of them being in the same phase, the number of ground states that matches. But the total Hilbert space doesn't necessarily have to match, just the number of excitations differ between these two models. And so if you want to write down some quantum circuit that interpolates between the two, you need to keep this into account. So we have to supplement this with ancillas. So if you denote this quantum circuit as some unitary going from D1 to D2, and you act on a string net state in D1, where you add in these ancillas initialized to 0, you find that your resulting state in D2 becomes entangled with these ancillas. Now you can disentangle this again, but because the Hilbert spaces don't match, there is no unitary way of doing this. But the main point is that, well, if I act again with this unitary, with the dagger, it's inverse, I just get the original thing. So this circuit is unitary on the full Hilbert space. So the conclusion there is that indeed, from the quantum information point of view, we can confirm that two string net models based on Morita equivalent fusion categories are indeed in the same phase. So that's like the first part, the first result of this. Now, secondly, a very nice application, I would say, of this quantum circuit and the fact that we can construct this is that the ground state component of the circuit, which itself is no longer a unitary, it's some projector which projects onto the ground state. It also provides a tensor network representation of the ground state of D2 that now depends on the choice of this M. So you get this, similarly to before, you get this kind of quantum circuit, which if you act with it on some trivial state, you just get a tensor network representation of the ground state. But this now depends on the choice of this module category M. So there's some freedom in this choice of tensor network representation depending on this choice of module category M. And this construction essentially generalizes the previously known tensor network representations of this ground state. Now, why is this interesting? Well, okay, these tensor network representations of string net states, they have the property that they have string-like symmetries on the virtual level. So there are these operators denoted in red here, represented as matrix product operators that you can move freely through the lattice. And the existence of these operators you can kind of see from the fact that if you have such objects, you can explain things like the ground state degeneracy, because you can imagine that, okay, I can now, if I put this thing on a torus and I put these matrix product operators on the virtual level, I can move these wherever I want. So my Hamiltonian, being a local operator, doesn't see these. So all these states have the same ground state, have the same energy. But these things are distinct. I cannot deform one into the other without doing something very non-local. Similarly, anionic excitations are explained in this language by saying that you have some excitation with one of these matrix product operators attached, and this non-local aspect of these excitations is what makes them have these fractional statistics, non-trivial braiding properties. Now, these MPO symmetries have to satisfy various consistency conditions. This is you just derive this from the fact that these operators, they should be able to move freely through the lattice. So if you just sit down, use the theory of tensor networks, and you derive all the consistency equations that come out of this, you get these 6 conditions. The first 2 of which are already present because these are supposed to be, well, we already know what the solutions to these are just because of our quantum circuits. And then the point is that the remainder of these equations can be solved by using the remaining pieces of this bimodular category. So that's kind of the second main result that we have is that this consistency conditions for having these virtual symmetries in these tensor network representations coincide with these pentagon equations of some bimodular category. Now, I think the most cool application of this is that, well, so we stated that this quantum circuit provides you a way of generating dual tensor network representations of the same string net model. Now, what does this imply? If you go to the 1 + 1b boundary theories of these dual tensor network representations, these boundary theories are dual. So, for example, if you take the toric code and you look for some boundary theory of the toric code, we have 2 tensor network representations of the toric code. You would find 2 Kramers-Wanier dual Ising models as the boundary theories of these dual representations of the toric code. Other examples that you can generate like this very easily are the Jordan-Ring transformation. Actually, something you can also understand in this language. Something called the IRF vertex correspondence. This is some correspondence between solid on solid model and the 6 vertex model. If you know this, then you will recognize this. Something like the Kennedy-Tasaki duality, which is a duality between an SPT phase and just a regular symmetry broken phase. All of this fits perfectly well within this framework. And the global symmetries of these boundary theories are then just given by the dual virtual symmetries of the string net model to which they are attached. So this is kind of the second conclusion, and basically the conclusion of this talk is that these generalized tensor network representations for string net models provide you a systematic recipe for understanding symmetries and dualities in the quantum spin chains that live on the boundaries of these string net models. So with that, I would like to thank you for your attention.
Thank you very much. So please can hear you have questions.
Yeah, thanks for your talk. It's very clear. So I have a quick question. So if I understand correctly, the input category determine a boundary condition and extreme field center determine a bulk property.
Yes.
And your argument showed that in the bulk wave function, I can go from one to the other by finite depth circuit.
Yes.
I'm wondering what happened on the boundary. Does it mean I can go from one boundary condition to the other by?
Yeah, that's a good question. Indeed, so in the paper, we just restricted ourselves to closed manifolds without boundaries, just because it was the easiest thing to do. If you want to include boundaries, or more generally domain walls, the problem is that the category theory kind of becomes a bit more involved, because you can imagine you have one string net model here, another string net model here, and you want to go to some other string net model here and some other. So in total, you have 4 fusion categories there. Something like 6 bimodule categories connecting all of them, and so you need to work through all of this. But indeed, yes, you could. I suspect that it's perfectly doable to indeed go from one boundary condition to another boundary condition. Should be doable, yeah.
Thank you.
So you showed that if there's a Morita equivalence, then they're in the same phase.
Yes.
Does the reverse direction hold?
Very good question, indeed. So we've thought about this. If you take the point of view that a generic state. So what you're asking, if two states are related by a finite depth or a constant depth circuit, does this imply Morita equivalence? That's the question, right?
Yes, yes.
It should, in the sense that you can think of a generic state as just the fixed point state with some constant depth quantum circuit on top of it, inducing some correlations. So that's some unitary acting on the fixed point state. You have some other unitary acting on another fixed point state. You're given that these are related by a constant depth unitary, because that's your assumption, that's what you start out with. So in the end, you have some very big unitary acting on one string net state, giving you the other string net state. And then the thing left to prove is that this unitary corresponds to our circuit, actually. And this unitary has to specify some particular properties. It must play nicely with this RG fixed point property. And so probably from that, you can constrain this unitary to, in the end, arrive at exactly the circuit that we wrote down. I don't know if that was clear. It's really hard to explain this with my hand. So if you're,
Okay.
you can definitely talk about it after.
Yeah, sounds good.
Well, my question was kind of answered, but I have another one. Are there like some simple examples of categories that are Morita equivalent?
That are or are not?
That are.
Oh, for example, the category given by just a group and the representations of that group. These are Morita equivalents. For abelian groups, these things are the same, so that's kind of boring. But for something like S3, if you define a string based on S3, this thing has 6 elements. S3 has 6 elements, right? You can define a string model based on that. While rep S3 only has 3 elements. There's 3 reps of S3. And so these things look very different, but nevertheless, there is a constant depth circuit that goes from one to the other.
Does it count to take, I don't know if this counts as 2 categories, if you take the same fusion rules with different solutions to the
No, these are typically not.
That counts as the same category, or?
No, this counts as a different category.
And are these always?
No, they are typically not Morita equivalent.
Okay, because I know at some point Frank was wondering about that.
No.
So that's not true?
No, they are not. Okay. Genetically, certainly not. There probably are cases where it is, but genetically not.
So looking at the action of basically the inserting of the domain walls in the BP and the plaquette. So on the plaquette, you can have like a support representation of the tube algebra.
Oh yeah,
so can this be understood as some kind of action on that? And
so indeed, the more general construction of how to do this, including excitation, indeed involves this study of these tube algebras. And essentially, the only technical tool that we needed to do this is to look at modules of the tube algebra. So you have a tube algebra that acts on some module of the tube algebra. You have 2 tube algebras, and if you have a bimodule between these two tube algebras, then you can just do this, including excitations. So indeed, it's exactly that.
so that would be like tunneling excitations from one phase into the
Exactly.
other.
Yeah, exactly. Yeah.
Okay, so that's it. Let's thank Lorenz and all the speakers of the session.